This is review video 31, Maxwell Boltzmann distributions. So first of all, what even is that? It's a graph, and that graph is going to show us the kinetic energy of various chemical samples at different temperatures. So please recall that when we say kinetic energy, that's the energy of motion. So we're kind of more or less talking about how fast those samples are going and what proportion of molecules within a sample are going what speed. Specifically, we need that because we need to be able to use it to see if the majority of a sample is moving fast enough to overcome the activation energy requirements of a reaction. Because as we know, when particles move faster, they hit each other with more force and they are more likely to react. So here is an example of a Maxwell-Boltzmann distribution. And so what we're seeing here is we're seeing a couple of axes. Now the x-axis in a Maxwell-Boltzmann distribution is always going to be kinetic energy of some fashion. Generally, the units for that are going to be kilojoules per mole. The y-axis is going to be number of particles. So that could be molecules, it could be atoms, it could be whatever is participating in this reaction. But amount of particles is going to be your y-axis. All right, so looking at this graph, we're seeing three different lines. This red line here that I'm tracing right now, that line represents the sample that has the lowest overall temperature, which at first glance doesn't look like it would be a low temperature because it looks like it's the highest curve. So we're going to call that line 1. However, the reason that that represents the sample with the lowest temperature is because most of those molecules, so like all this area under the curve right here, all of that is moving pretty slowly. Because as we can see on the x-axis going in this direction, the farther you are that way, the more kinetic energy you have. And most of the molecules are grouped within this region. So you can see that that sample is moving the slowest. All right. Our blue line here that I'm about to trace represents a sample that has a mid-range temperature, so like a medium temperature. And we can see that because still a lot of them over here are moving pretty slow. But we can see that this blue line starts moving this way, and we can see a little bit more of that sample is moving a little bit faster. The green line, which I'm tracing right now, represents the sample with the highest temperature. And so while a good portion of them are still moving pretty slow over here, look how many of them are moving faster now, because we're talking about area under the curve. So if we consider that this vertical line represents the collision energy required to achieve activation, or our reaction to go, the green actually has the most that exceeds that line. Whereas the blue only had a little bit, and the red had even less. And those shaded regions that I just gave you represent molecules that can react. So again, the green, the highest temperature, has the largest amount of molecules in that sample that can achieve a reaction. The blue has a middle amount, and the red has a very, very small amount of molecules within that sample that have enough energy to hit each other and react. Okay? The key to understanding a Maxwell-Boltzmann distribution is that when we're looking at a sample at a particular temperature, not all of the molecules in that sample are going to have the exact same kinetic energy, because what temperature really is a way to measure the average kinetic energy in a sample. So if I look at this diagram over here, we can see all of these different molecules representing a sample at one temperature. But some of those molecules are moving pretty fast, represented by a large arrow, whereas some of them are moving pretty slowly. And so as an average, if we were to average all of the individual kinetic energies of those molecules, you would get a distribution that looks like one of these, meaning that on average, most of your molecules, like say in this red sample, are moving pretty slowly, but some of them are moving a little bit faster. Okay? So now I want to talk about catalysts and how they affect Maxwell-Boltzmann distributions. First of all, there's two main types of catalysts. A homogeneous catalyst, this one, that's specifically a catalyst where the phase the catalyst is in is the same as the reactants. So if I have reactants that are in liquid phase, the catalyst we use is going to be a liquid as well. A heterogeneous catalyst is when you have a reactant and the catalyst you use to catalyze the reaction is a different phase. So when I did the demo with the fog and we were decomposing hydrogen peroxide, I dumped in a solid, right? And since hydrogen peroxide is aqueous and the catalyst I used was a solid, those two are in different phases, therefore it's a heterogeneous catalyst. In terms of how that affects the distribution, it changes the activation energy requirement. And we know that already because that's what catalysts do. They provide an alternate mechanism with a different activation energy requirement. So, looking here, this yellow line represents the activation energy of a particular reaction without a catalyst. And this line right here represents the new activation energy with a catalyst. So we can see that that line has shifted. With our three samples, our red low temperature sample, our blue medium temperature sample, and our green high temperature sample, again, if we look at the area under the curve, the green has all of these molecules that could react without a catalyst, but with a catalyst, way more, right? Way more of them can react because what the catalyst has done is it's shifted down the energy requirement of the reaction. For the red one, the low temperature, there was barely any molecules that could have reacted originally. But with a catalyst, even at a lower temperature, now we have way more molecules that could achieve a successful reaction. And again, the same with the blue. We have all of these normally, but when we added a catalyst, it shifted so that more of them can react. And so looking at this distribution versus what we've already talked about, the potential energy diagrams, why would you need to use a Maxwell-Boltzmann when you already know how to use a potential energy? Well, because the Maxwell-Boltzmann distribution is going to show different temperatures and different amounts of molecules, whereas the potential energy diagram only shows energy changes over the course of the reaction. And yeah, both of them can show activation energy potentially. However, this one is going to actually allow you to evaluate how much of a sample could react successfully, whereas this one just kind of gives you an arbitrary amount of energy that is necessary, but it doesn't tell you anything about a particular sample. So if you have any questions about interpreting Maxwell-Boltzmann distributions, please let me know.